Here in this video we will derive the expression of capacitance of a parallel plate capacitor. An ideal capacitor is such an arrangement which provides a larger capacity in a smaller space, and the parallel plate capacitor is the most commonly used capacitor. See, here is the diagram of a parallel plate capacitor. Here in this diagram there are two plates. These two are the conducting plates, the plate A and the plate B. The plate A is given positive charge. That is, if a charge plus Q, suppose plus Q amount of charge is given to plate A, so that minus Q charge is induced on left face of the plate B and plus Q charge is induced at the right face of the B. See, here we have given positive charge to the plate A, and due to this, as the plate B is nearer to the plate A, so a negative charge will induced at the inner side or left side of the plate B, and positive charge will induced at the right side or outer side of this plate B. Now see, this plate B is earth. This is the earthing. So as the plate B is earth, so these plus Q charge will move to the earth. Okay, any amount of positive charge on the plate B will move to the earth. So see, so there is no positive charge on the plate B, there is only negative charge on the plate B now, as the plate B is earth. Okay. Now we will derive the expression of capacitance of a parallel plate capacitor when the space between the two plates is filled with air or vacuum. So first we will derive the expression of capacitance of a parallel plate capacitor when there is air medium in between the two plates. So the first derivation is about, let us write it as a capacitance of a parallel plate capacitor with air in between the two plates. So first we derive the capacitance of a parallel plate capacitor when there is air medium between the two plates. That is, this area is filled with the air medium. See, already we derived in our electric field chapter that the electric field inside two oppositely charged conducting plates. So see, it is positively charged, it is negatively charged. So electric field inside these two plates, E is equal to sigma divided by epsilon naught. Already we derived this expression where sigma is the surface charge density and the value of sigma is equal to Q divided by A, where A is the cross-sectional area of each plate and Q is the charge on the plate. Okay, already we derived this expression in the chapter electric field. Now and the direction of the electric field is along this direction. This is a uniform field inside this these two plates or inside the There is a uniform field inside the two plates of the capacitor, and the magnitude of the field is E is equal to sigma by epsilon naught, and this is the direction of the field. Okay. Now let us start our derivation. Let us consider two parallel plates A and B separated by distance d apart. Plate A is charged with a charge plus Q, and the plate B is earthed. Okay. Now already we derived the expression of electric field inside the two plates of the capacitor in the chapter electric field. So let us write that one. If sigma is the surface charge density of the plates of the capacitor, then electric field between the plates that is E is equal to magnitude of the electric field E is equal to sigma divided by epsilon naught, where epsilon naught is the permittivity of the free space and sigma is the surface charge density. Let P be any arbitrary point inside the plates of this capacitor. See, the direction of the electric field at the point P is along this direction. So, if dV, the small potential, is the difference of potential between two closely situated points around P, then say here we will do the integration to find the final value. So if dV is the difference of potential between two closely situated points around P, then we already know from the definition that potential is equal to negative line integral of the electric field intensity. So dV is equal to, potential is a scalar quantity, is equal to minus E dot dr. By the definition of potential, we know that potential is the negative line integral of the electric field intensity. Also we know that the work done to move a unit positive charge against the electric field is called the electric potential. So see here, if we move a unit positive charge against this electric field, then the angle between E and dr must be, because they are in opposite direction, or we are moving a unit positive charge against the electric field. So the angle between these two vectors will be 180 degree. So minus E dr cos 180 degree. Again we know that cos 180 degree is equal to minus 1. So minus E dr into minus 1. So this is equal to E into dr. Now the potential difference between the two plates of the capacitor, the separation between the two plates of the capacitor is d, small d. So here we have taken the potential difference between two closely spaced points inside the plates of the capacitor. Now the potential between the two plates of the capacitor. Now to find the potential between the two plates of the capacitor, we have to integrate this one. So see, this implies V, or the potential between the two plates of the capacitor, is equal to integration of this dV, 0 to V limit is equal to E dr. Integration, see, it is the, now we have to integrate E dr. See, the limit will be 0 to d, because the maximum space is d, the separation between the two plates. So again we know that E here, in this case, E is a constant quantity, it is not a variable, because sigma is a constant quantity, surface charge density, and epsilon naught is also a constant quantity. So E, as it is a constant quantity, it will come out of the integration, so 0 to d. So this is equal to E. Now integration of dr is equal to r, and the limit is 0 to d. So E into d. But already we know that E is a sigma by epsilon naught. So sigma d divided by epsilon naught. But again we know that sigma is the surface charge density, and its value is equal to Q by A, where A is the cross sectional area of the plates of the capacitor. So this is equal to Q d divided by epsilon naught into A. See, here we replace this sigma by Q and A. Now capacity is equal to, or capacitance of this parallel plate capacitor, capacitance is equal to, that is capacitance is equal to charge divided by potential. Already we know from the definition, charge divided by potential is the capacitance. That is, this implies C is equal to charge. Here charge is Q divided by potential is QD divided by epsilon naught A. QD divided by epsilon naught into A. So this is equal to this, the Q will be cancelled out. So epsilon naught A divided by D. That is capacitance of a parallel plate capacitor when the air medium between the two plates is epsilon naught A divided by D. See, from this expression we can conclude that the capacitance of a parallel plate capacitor when an air medium in between the two plates is directly proportional to the cross-sectional area of the two plates, and capacitance is inversely proportional to the separation between the two plates.